Welcome back, students. This is the final lesson on the trigonometry of arbitrary triangles. Here we're going to prove the law of sines, the law of cosines, and if we have time, Heron's formula. In the first video, we went through some review on trigonometric functions and then some right angle trigonometry. We also had some overview of the law of sines, the law of cosines, and then arbitrary triangle cases as well. In the next three videos, we actually went through the law of sines and law of cosines and the applications. But we didn't spend too much time on the proofs. Here, we're going to do that. Okay, let's move on to the law of sines. And it goes kind of like this. Acute triangle is easier, so let's get acute angle first, and then after that we're going to go over to obtuse triangle. I keep getting unlucky. Okay, looks like this is an acute triangle. Alright, and let's suppose we have triangle ABC, and we say capital A, capital B, capital C correspond to the size of the internal angles, and small a, small b, and small c are the lengths of their opposite sides. Now, how do we prove the law of sine, which go like this? Sine of capital A over small a is equal to sine of capital B over small b is equal to sine of capital C over small c. We begin with drawing a vertical line from the top angle A and thus creating a couple of right triangles as you see here. And we did a color coding, the red triangle ARC and the blue triangle ARB. Now from the red triangle, please make this observation. B is the hypotenuse and H is the opposite angle of the angle capital C. So what do we have? H over B is sine of capital C, and consequently H is equal to B sine of capital C. That comes from the red triangle, so I did the color coding accordingly. Now let's move on to the blue triangle. Triangle ARB. Here hypotenuse is C and the opposite side of the angle B is H. So what we have, H over C is sine of capital B, consequently H is C sine of B. Now we are ready. Both of them are the same. Both of them represent the same quantity H, so set these two equal. What do we get? B sine of capital C is equal to C sine of capital B, and therefore dividing both of them by small bc we get the desired result. Sine of capital C is equal to sine of capital C over small c, is equal to sine of capital B over small b. We ended up proving one of the two equalities that we have to prove here. How about the second equality? All we have to do is to change the viewpoint or tilt the triangle and draw a vertical line from, let's say, angle C, and then consider a couple of right triangle ACR and BCR. We're going to end up with the corresponding result. Sine of capital A over small a is equal to sine of capital B over small b. And if you repeat the same thing from the angle capital B and draw the triangles and then draw the right triangles to do the same thing, you're going to get sine of capital A over small a is equal to sine of capital C over small c. In any case, it's just a repetition. In other words, we prove the law of sine as long as everything is acute. Now what if we have an obtuse triangle? Well, it's pretty much the same as a matter of fact. Let's go with this one. And we have a triangle like this, and we use a bit of a color coding, but it may not be correct to get this red formula here from red triangle as a matter of fact, because it's not really a right angle trigonometry. It's closer to inscribing this picture to coordinate axes. What am I talking about here? Let's go over to the definition of trigonometric functions, and let's consider the obtuse angle case. Okay, here's an example. When the angle is greater than 90 degrees but less than 180 degrees, if we have obtuse angle, we can have an inscribed triangle, red triangle, kind of like this, which is pretty much the same as this kind of situation. And the labeling should be C is my origin, and A is gonna be, capital A is gonna be the terminal point of this on the circle of radius B. So sine of capital C is vertical over radius, which is h over b. So the same thing all over again, and thus h is equal to b sine of c, the same result as before. Different picture and different argument because this is an obtuse case, but same result again. How about the blue one? Well, we have to look at the right triangle ARB, which is a big triangle given by the outline. Height h is the opposite of the angle capital B, and c, small c, is the hypotenuse. So what do we get? H over c is sine of capital B. H is equal to c sine of B. So what do we have? Same result as before. Setting these two equal, we're going to get this algebraic equation, and consequently we get the same algebraic manipulation to get the same algebraic result. So pictures may be different, but algebra from that point on are identical. Consequently, we have the same result even when my triangle is obtuse. Of course, I don't have to consider two obtuse angles for the same triangle, because obtuse triangle can have only one obtuse angle, because the internal angles of triangles must add up to 180 degrees. You cannot have two obtuse angles there. Okay. The law of sine is done, and let's move on to law of cosines. And let's consider an arbitrary triangle. Again, acute angle case is a bit easier, so let's do that one first. So we have an acute triangle kind of like that, and then from the top angle capital A, let's draw a vertical line to create a couple of right triangle, as you can see over here. Okay, in this case what do we have? From the blue triangle ACR, we have hypotenuse B and height h, and horizontal is going to be CR. The red right triangle has hypotenuse C and height h, and horizontal is BR. From the blue right triangle, this is what we're going to do. We're going to take Pythagorean formula. AC squared is equal to AI squared plus CR squared from Pythagorean formula. But AC is equal to B, isn't it? So hypotenuse is B squared, and then AR is height, H. So we have H squared. Now finally, what is CR? The distance between C and R, that's the distance between C and all the way to B minus the distance from BR. Consequently, we have that. But CB, that distance is actually the same as small a, so we can re-express it as B squared is equal to H squared plus A minus BR, total quantity squared. Okay, now let's move on to the red triangle. In the previous case, this BR is a little ugly, so let's represent this BR in terms of, well, A, B, and C. And here we go. Cosine of angle capital B is BR over C, because BR is adjacent. So what do we have? This BR can be written as C cosine of capital B. So we're going to replace this BR by C cosine of capital B. One more thing. In this red triangle, H is the opposite. So H over C, opposite of hypotenuse, is sine of B. Consequently, H can be rewritten as C sine of capital B. So this one will be replaced by C sine of capital B. This one, as we said before, will be replaced by C cosine of B. if you do that, here we go. Let's see. From the Pythagorean formula, we have h squared plus cr squared, and cr squared is actually abr squared, and h squared, as we observed before, is c sine of b total quantity squared. And then the next, let's see, a minus br is the same as a minus c cosine of b, so we have that square. So what do we have? B squared is equal to c sine of b total quantity squared plus a minus c cosine of b total quantity squared. From this point on, you don't have to look at the picture, just algebraically manipulate everything. Take the squared, take the complete squared, and make this observation. Sine squared plus cosine squared is equal to 1, so c squared sine squared b plus c squared cosine squared b is equal to just c squared times 1. The others, a squared minus ac cosine of b, stay the same, so they just stay the same, and what we have the desired result. B squared is equal to a squared plus c squared minus 2ac cosine of capital B. Now, if you want to prove the other two identities of the law of cosines, what do? Well, just change the viewpoint or tilt the triangles and do exactly the same thing. Get this vertical line from the angle C and get the vertical line from angle B and repeat the same processes, and you're going to get the same results because they're all symmetric, they're all identical in terms of what's the angle, what are the other sides, and what's the opposite. So you don't really have to do the same thing 3 times. Just you can say that all you need to do is tilt the triangle. In other words, we completed the proof of the law of cosines as long as we have an acute triangle. Now, what if we have an obtuse triangle? That's the second thing we'll have to do. Well, okay, we are lucky, we have this kind of thing. Okay, we have an obtuse triangle, then what do? Well, only one obtuse angle matters. The other two are acute angles, so you can do pretty much the same thing as before. But if you have obtuse angle, kind of like this is what we're going to end up with. From this blue triangle, we have the same Pythagorean formula. Hypotenuse squared is vertical squared plus horizontal squared. And horizontal is height h, so h squared. And then horizontal, cr squared, that's a little bit tricky. Cr is now br minus bc, because br is the big distance here. Then a, small a, is just going from BC. Do you see that? This is the same as BR minus BC. Then you're going to get the CR, the horizontal side for this blue triangle. But BC is equal to A, so we get this result. And compare that with the previous case where we have acute triangle. Everything is the same except for A minus BR versus BR minus A. But then again, experienced students will see that makes absolutely no difference because we're going to take squared anyway. Let's go back. Anyway, let's look at the triangle. This time we have to look at a big triangle. I cannot draw the red triangle, otherwise it's going to just go right on top of all this. So what do we have? BR is the big horizontal, so that's the adjacent side of this capital B. And therefore, we have this BR is equal to C cosine of capital B. C is the hypotenuse. And also, H is the opposite, so H over C is sine of B. Consequently, H is equal to C sine of capital B. Now we are ready to plug everything into this one. So what do we have? H is C sine of B, so C sine of B total quantity squared. And then this CR squared, which is BR minus A squared, but BR is C cosine of B, so we have C cosine of B minus A total quantity squared. From this point on, it is nothing more than algebraic manipulation. Just use complete square formula to break everything up. And then please note that sine squared plus cosine squared is equal to 1. So c squared times 1, we have just c squared. In the end, we have exactly the same result as before. No wonder, the only difference was the sign difference here, which shall be eliminated by taking squared.